Hi everyone. Today we'll see why and how to convince stakeholders to use 3D printing in the plastic injection industry. By the end of this webinar, you will have learned how to make conformal cooling a reality in your business. In particular, we will review the top 3 use cases of 3D printing in the plastic injection industry, including conformal cooling, which is one of the most beneficial approach. We will also learn about the challenges still preventing the adoption of conformal cooling and how you can address them. We will then review the business case aspects, which is one of the last overlooked challenge of 3D printing. Finally, you will learn how front-end simulation can help you build such strong business cases and justify the additional investment associated with Conformal. So my name is Arnolds, and I'm Innovation Director at Maya HTT. Before joining Maya, I worked for almost 10 years in the manufacturing industry. In particular, I participated in several R&D projects on metal 3D printing and composite manufacturing, especially focusing on the transition from engineering to the shop floor. I'm now working for Maya HTT, which is an engineering software development company with more than 40 years of software experience. We have developed over 35 software modules for Siemens, which are now used by close to 7 million users worldwide. Several hundreds of our customers are located in North America and Europe, mostly engineering firms developing innovative products, but also manufacturing companies helping them make those products. Our team's experience covers many different industries, including discrete manufacturing. And in particular, we have performed analysis for our plastic injection customers, but we went even further and developed automated tools to help them gain efficiency in their mold design process. We have also helped many companies to implement metal and plastic 3D printing as part of their engineering and manufacturing processes. This allowed us to gain critical knowledge in the plastic injection industry that we are leveraging today. So let's talk about 3D printing in the plastic injection industry. When we look at numbers, we see that the use of 3D printing in the molds and tooling sector was evaluated at more than $5 billion in 2020 and is expected to grow to 20 billion in 2030. Those are big numbers, meaning that many people are using 3D printing for molds and tools. Now, let's look at what they're doing. Overall, 3D printing is a very broad term covering multiple technologies which can be used in many different ways, including in the plastic industry. However, to get most out of the 3D printing technology, we need to change the way we approach part design, material selection, part performances, manufacturing, supply chain, etc. With so many questions, it can be daunting to identify how to best use 3D printing in the plastic injection industry. So let's review these aspects in detail so you can decide how to best leverage this exciting new technology in your business. At high level, 3D printing and plastic injection are two completely different manufacturing processes. Each has its own strengths and weaknesses, which are summarized here. Plastic injection is a very fast process, able to produce a large number of identical parts at low cost and very quickly. 3D printing, on the other hand, is very flexible and offers many advantages over traditional manufacturing techniques, like the ability to cope with multiple design changes. It also enables entirely new design concepts by removing many design constraints for the part designer. We identified several approaches to leverage the benefits of 3D printing, that is flexibility and time to market, to improve the plastic injection industry. The top 3 are the following. The first approach, the one that is the most disrupting, is to entirely replace the injection process by 3D printing. It means print the part instead of injecting it. Several aspects are listed here. At high level, the concept is to skip the metal mold entirely. This significantly reduces the time to market and the tooling cost. It also hugely improves the ability to make changes in the part. With this approach, you can get parts in less than 2 weeks. However, 3D printing is slow. That's why this approach is currently mostly used for prototyping, where you need to easily change the part design and quickly get feedbacks. This approach has been widely adopted in the industry, and the use of 3D printing for prototyping was estimated at more than $4 billion in 2020. To account for the shortcomings of the previous method, some companies like 45-3D have proposed a hybrid method. With this concept, the parts are made by injection molding, but using 3D printed molds. With this approach, you can still get your first parts within a few weeks, which is significantly faster than the traditional injection process, and you keep the ability to easily modify your parts. However, each mold can only produce up to 500 parts, and the parts are somehow slow to produce with cooling times longer than 2 minutes. This makes it a great approach for small, early production series. The third approach is to use the traditional metal molds, but with 3D printed mold components in metal. Those components leverage the design freedom of 3D printing to reduce the injection process cycle time, for example. That's the famous conformal cooling approach. Printing the entire mold in metal would be way too expensive and inefficient. The proposed approach used 3D printing where it adds the most value. The lead time is similar to traditional injection molding at a minimum of 8 weeks. While this method increases the tooling cost, it significantly reduces the cycle time, generating large cost saving for the molder. The good news is that the three approaches presented don't compete against each other. They can actually be complementary and used on the same part, but at different stages of development, depending on the need for design change and the acceptable manufacturing cost. Let me explain. Early, during the part design, 3D printing the part enables to quickly collect feedback on form, fit, and function, and iterate on the part concept. Later, during the initial stages of manufacturing, potentially in parallel with the steel mold being designed, 3D printing the plastic mold can enable you to put realistic parts very early in the hands of your customers to collect feedback. Later, once the steel mold is in production, conformal cooling inserts reduces the production cycle time, enable the molder to produce more parts faster and cheaper. So overall, 3D printing can help improve the plastic injection process at different stages. Now, let's consider more in detail the third use case, the conformal cooling approach. As it's the one used during production, it has the largest economical impact on the industry. This technology consists of using 3D printing to create metal inserts with special cooling channels, bringing water very close to the part as it can be seen on the image to the right. This is quite helpful to extract heat from local hotspots that conventionally drilled cooling lines can't handle. This technology has several key advantages. First, it enables significant cooling time reduction by removing heat locally. In some cases, cooling time is reduced by up to 50%, which is significant for molders, leading to larger profits, but it also frees manufacturing capability earlier. Conformal cooling can also lead to a more uniform part temperature, reducing the risk of parts getting defects like warpage and sink marks. Finally, as conformal cooling inserts are self-contained, molds are simpler, and you no longer need to install and test plugs and diverters. This reduces the risk of errors. Although it has many advantages, conformal cooling also has key challenges. One that quickly comes to mind is related to the fact that conformal cooling leads to much more complex designs. Because it removes many design constraints, the designer ends up with way more design options than for conventional cooling, and this significantly increases the number of decisions that the designer needs to make. With conformal cooling channels, the designer has to choose the section geometry, which no longer has to be cylindrical. Actually, diamond-shaped and water drop-shaped channels are recommended for printing. The designer also has to choose the channel shape itself, which no longer has to be straight. Therefore, the channel locations are way more diverse than what is done with drilled water lines, as it can be seen on this image. But 3D printing has its own new manufacturing constraints that need to be accounted for. The good news is that many design for additive manufacturing tools and trainings are now available on the market to help the designers adjust this challenge. Actually, we talked to several mold designers who complained that the newly graduated designers know better how to design a part for 3D printing than for the injection molding. In parallel, 3D printing also comes with new material. Most of the traditional mold steels are not available for 3D printing, so the designer has to choose amongst new material with new properties. Several of those metals are less corrosion resistant, so the designer needs to account for the durability of the insert during the design. Here again, a wealth of information is provided by the materials OEM, and over the last few years, we noticed the development of new same-as material with different chemical composition, but similar behavior to the raw material, making it easier for the designer to choose what material. Finally, more than 2 million 3D printing machines were sold worldwide in 2021, and there is now more than 200 3D printing services companies in the US pushing to reduce price and lead time. Overall, The industry is getting more and more mature, and it's becoming easier and easier to find suppliers to produce parts at low cost. However, due to the price of the machine, the metal powder, and the fusion rates of the machines, the parts remains expensive. Robustness and reliability of the machines are still limited, but they are seriously being considered. In the past years, venture capital funds invested more than $300 million in 3D printing startups, coming up with new machines and new material to further push down part cost and lead time. So all those challenges could explain the slow adoption of conformal cooling, but as it was mentioned, several options are available for each of them. When talking to a mold maker CEO, he pinpointed another challenge for which there is not a lot of solution available. It all comes down to business justification. Bottom line, metal 3D printing is still expensive, and a conformal cooling insert is an additional cost for the molder. A typical 3D printed part will cost between $5,000 and $10,000 to print and finish. Being smaller, conformal cooling inserts tend to be cheaper. However, they enable molders to reduce cycle time by up to 50%, and therefore to produce more parts with the same time frame and with the same equipment, leading to increased revenues. However, everybody knows it's hard to build a business case. But in our situation, it's even worse because the technology is new. Molders and mold makers are still learning when it's relevant to use conformal cooling and when it's not. There are two main approaches used currently to decide whether conformal cooling should be used or not. The first one is leap of faith. Here, the molder assumes that conformal cooling will generate enough benefit. He assumes that the conformal cooling channels are properly designed, and he asks the mold maker to have the insert printed at high cost. Once printed, the inserts are tested to validate whether or not a relevant cycle time saving is achieved. This approach is very risky, but reduces delays and cost. Due to the high cost of the printing process, most of the time, there is no design iteration. The second approach is the scientific method. In this case, the mold maker has a full mold flow simulation performed, adding delays and costs to the process to evaluate the potential cycle time saving. If the business case built on the simulation data is positive, then the inserts are printed and tested to confirm the actual cycle time reduction. This approach is way less risky, as the insert would only be printed if the business case is positive, but the cost and delays of the mold flow analysis penalize the business case and prevent optimization. So up to now, molders and mold makers had to choose between high risk, low cost and medium risk, medium cost approaches. Lately, a new approach has been developed which could change this situation. It offers a low risk, low cost alternative. This approach is called front-end simulation. But what is front-end simulation? Front-end simulation is basically making the mold flow analysis accessible to professionals without simulation expertise. When a project manager is making decision on whether or not to use conformal cooling, or when a designer is creating the conformal cooling lines, instead of relying only on experience, which is still scarce for this technology, it's better if they have numbers and facts to back their decisions. Because it's meant to be used iteratively during the design process, front-end simulation tools tend to be very efficient, extremely fast, and provide numbers and facts within minutes. They're also usually very easy to set up and quite affordable. So what does front-end simulation looks like? This is SimForm, an example of a front-end simulation tool. When targeted at cooling time prediction, typical front-end simulation usually allows the project manager and the mold designer to quickly and easily assess the cooling time of a given mold. But it also enables them to easily run what-if scenarios. That is, compare different cooling concepts to decide on the location of the cooling lines and assess if conformal cooling or baffles, bubblers, mold marks, etc. are relevant. Overall, front-end simulation tools like SimForm helps you to reduce the development risk by preventing bad surprises when testing conformal cooling. This leads to a reduced development lead time and cost by avoiding design iteration and unnecessary 3D printing costs. Let's now consider how front-end simulation can enhance conformal cooling. In this context, we start with a mold with existing cooling lines. We want to assess the cooling time reduction that could be achieved by using 3D printed inserts. This reduction will drive the business case to justify additional investments. When considering 3D printed inserts, several aspects need to be addressed, in particular the location of the inserts and the design of the cooling lines. A front-end simulation tools like SimForm will enable you to quickly and easily assess the cooling time reduction you can get with conformal cooling inserts. You can start with a baseline mode with straight cooling lines, as we see here. Using SimForm, in less than 10 minutes, you get an estimation of the cooling time. Here it's 106 seconds, but also the cooling time bottleneck. In this case, those are the area in red. Those areas are the one that will cool last and then drive the business case, the cooling time. We might then want to update the design with conformal cooling inserts. Once again, within a few minutes, you can import the design of your conformal cooling inserts, run a new scenario, and get a new estimation for the cooling time. In this case, with the conformal cooling insert selected, the cooling time can be reduced by about 40%, which is huge for the model. However, keep in mind that conformal cooling is not a silver bullet. In this case, it looks like it's actually cooling too much. With the traditional cooling lines, upon ejection, the part temperature ranges from 65 to 105 degrees Celsius, with the hot section being in the central stiffener. However, with the conformal cooling, we observe that the central stiffener is much cooler. The new part temperature upon ejection ranges from 45 to 105 degrees C, and that's a bigger temperature gradient than without the inserts, meaning that the risk of Vedic warpage is increased. With this information, the designer could adjust the insert of the insert design to avoid overcooling. With all that data, the molders and mold maker could decide if there is a real risk of getting part defects and if the cycle time reduction is enough to justify investing in 3D printing inserts. How would they do that? As we just saw, front-end simulation tools enable the project manager and mold maker to estimate the potential cycle time reduction delivered by conformal. This is very helpful to build a reliable business case. To build such a business case, we start with a reference state with the traditional mold with its mold cost and cooling time. With the data available, we can calculate the total investment and the total daily revenue for this mold. We can then consider the conformal cooling inserts. We account for the increased tooling cost and the reduced cycle time, which increase the press production capability, enabling the molder to produce more parts with the same equipment in the same time period. As mentioned earlier, designing a conformal cooling insert is a bit more tedious than for traditional mold, so we accounted for a 15% increase in the design effort. Regarding simulation cost, with SimForm pay-per-use model, the cost of the assessment is quite low. It doesn't really impact the business case, contrary to a full mold flow simulation, which is overkill in the current situation. We can then calculate the new total investment and the new total daily revenue for a mold with conformal cooling inserts. By comparing the additional investment and additional revenues, it's possible to calculate the return on investment. We can see that in this specific case, the return on investment is very short, meaning significant and fast benefits for the molder on the short, medium, and long term. This should be enough to justify the additional investment. Overall, front-end simulation enables you to reduce the uncertainty on the cycle time reduction without adding significant delays and costs to your evaluation. This helps you build a strong, reliable business case easily. And this approach can be extended to many other changes like cooling lines cleaning, adding new water lines, adding baffles or bubblers, adding new high conductivity inserts like mold mask. With front-end simulation, it's possible to estimate the cycle time reduction associated with each approach. By knowing the additional cost of each, it's possible to build a business case, but even more, it's possible to rank the different strategies depending on the budget constraints and on the cycle time reduction targeted, as it's shown in this graph. All of this can be done without additional complex or expensive tool. So to conclude this webinar, we gave a quick overview of 3D printed technology, and we presented 3 different ways 3D printing can be leveraged to improve the plastic injection industry. All of those approaches can help you depending on the maturity of your product between quick prototyping and improvement of your established manufacturing process. We then looked at conformal cooling and how it can help the plastic injection industry reduces its production cost. This new technology also comes with challenges and fears that we summarized. We identified one often overlooked challenge, which is still difficult, which is the difficulty to build a strong business case to justify the additional investment required to get the significant cycle time reduction that conformal cooling can bring. We then showed that front-end simulation is a great tool to quickly and easily build those reliable business cases and to justify the use of conformal cooling. This new approach is also helpful for other situations, like during continuous improvement, as it helps assess the potential improvement of different strategies. As front-end simulation tools like SimForm are inherently made for non-simulation experts, they are easy to use, quick to set up, and provide reliable answers quickly and at very low price. During this webinar, we use SimForm as an example to illustrate the benefits of front-end simulation. If you want more information about front-end simulation in general, or more specifically about SimForm, please visit our website directly. You will be able to try this new type of tool by yourself through our free trial. And with that, I want to thank you for attending this webinar. Have a nice day.